When the lights dimmed in the auditorium at the NASA Press Center and the broadcast countdown on the screens reached 0, I prepared myself in the same way I always do before encountering fresh scientific data. I took a deep breath, cleared my mind, and mentally put aside everything I thought I already knew. Assumptions, theories, past interpretations, statistical expectations, and favored models were all placed into a separate mental box. The only thing that mattered in that moment was the evidence that would soon be presented. That has always been my method, because in astronomy, the universe constantly has the potential to embarrass us. It has done so before, and it will do so again. But humility protects the scientist, and that morning, I needed it more than ever. NASA's announcement had been anticipated for weeks. Rumors had swirled through university hallways, Slack research groups, and observatory networks around the world that the new object known unofficially as 3I Atlas had revealed something extraordinary. No leaks had emerged from inside the mission teams, but the sheer number of spacecraft involved in the observation campaign told its own story. Hubble, Webb, SOHO, MAVEN, Lucy, Psyche, MARO, Punch, Stereo, and several others had all contributed data. More than 15 independent scientific instruments across multiple platforms had been aimed at this single traveler. That alone would have been unprecedented. There had never been a coordinated observation of an interstellar object on this scale, not even for the first 2 visitors from beyond our solar system. The screen shifted to the first slide, and the presenters began. The images appeared in Sequence Webb's higher-resolution infrared captures, Hubble's wide-field visuals, MAVEN's ultraviolet cloud profile, MRO's high-rise data, Stereo's faint scattered brightness reports, and several others that flickered past with polished transitions. As each scientist stepped up to the podium, they displayed halos, fuzzed-out glare patterns, tails of various angles, and spectrum readouts that seemed interesting enough. Yet as the slideshow progressed, I felt something unusual, something missing. I waited for a simple detail, the foundation for every major calculation involving comet behavior, the size of the nucleus. I waited 1 slide, then 2, then 5. Surely the next one would contain it. It did not. Instead, they shifted to thermal data from SBHRX, halo expansion characteristics from MAVEN, dust modeling predictions from Lucy, and changes in tail reflectivity during solar wind rotation. All useful, all interesting, but all missing the single number that defines everything else: how large the object actually is. It was a silence that, to anyone familiar with comet physics, shouted louder than anything said aloud. The size of a comet is not trivia. It is the anchor point from which every other quantity flows. If you do not know the size of the nucleus, you cannot properly estimate mass, density, outgassing rate, expected dissipation, jet momentum, or non-gravitational trajectory shifts. It is not an optional detail. It is the first question any undergraduate in planetary sciences would ask. And here, among the world's most experienced astrophysicists, not one reference was being made to it. Not even casually. Not even indirectly. It was as if the subject itself had been quarantined and placed behind glass. That omission told me far more than any slide could have, because based on the limited public data already released over the past week, Webb's surface brightness falloff, MAVEN's hydrogen halo expansion radius, Psyche's subtle tracking anomaly, and the MRO reflective profile, it had already become clear to independent researchers that this object was not simply a larger version of Oumuamua or Borisov. It was orders of magnitude larger, the kind of size difference that forces science to stop, recalculate, and reconsider assumptions from the ground up. In 2017, Oumuamua, the first interstellar visitor ever detected, was estimated to be less than 200 meters long, roughly the size of a football stadium. In 2019, Comet 2I Borisov arrived and shocked astronomers by being approximately 1 kilometer wide, surprisingly large for an interstellar object, but still within the outer boundaries of known formation models. That, everyone agreed, was already strange, since smaller objects should statistically be much more common. Yet now, with only the 3rd detection of an object entering our solar system from another star, we were encountering something not slightly larger, not moderately larger, but potentially thousands of times more massive than Borisov and perhaps over 1 million times greater in mass than Oumuamua. This is not a small difference. It is a cataclysmic one. In astrophysics, when you have only 3 data points, and the 3rd differs from the first by a factor of 1 million, you do not simply shrug and move on. You pause everything, examine what you think you know, and ask how such an object could exist, let alone reach us. Statistically, the problem becomes even sharper. If interstellar objects drift freely between star systems, ejected randomly from planetary formation debris fields, then smaller objects should vastly outnumber large ones. One would expect to detect thousands of Oumuamua-sized rocks before stumbling upon something the scale of 3I Atlas. Instead, our 3rd object is the largest of all. This does not mean something paranormal or conspiratorial. It means our models are missing something fundamental. Either our assumptions about the number, distribution, and ejection mechanisms of interstellar debris are flawed, or this particular object is not the result of the normal planetary scattering processes we understand. Yet the press conference behaved as though nothing unusual had occurred. The tone remained comfortable, measured, institutional. Images were demonstrated, data was displayed, structural notes were read, but no one dared address the elephant or, rather, the mountain in the room. That silence made the data even louder. When institutions avoid describing something, it usually means they are not yet prepared to deal with the consequences of acknowledging it. But the size was only one remarkable element. There was also the matter of arrival geometry. 3I Atlas had entered the solar system on a trajectory nearly perfectly aligned with the ecliptic plana flat disk in which the planets orbit the Sun. This may seem insignificant to the general public, but in celestial mechanics, it is astonishingly unlikely. Only a small fraction, perhaps 1 in several hundred of incoming objects from interstellar space should happen to intersect that narrow band. Most should approach from above or below at random inclinations. Yet this one came in almost perfectly parallel, as if accounting for our solar system's orientation. That alignment was not only statistically rare, it conveniently placed the object within continuous view of nearly every major telescope humanity currently operates. Observatories in space and on the ground could track it for weeks without blind zones, without solar interference, and without missing key rotation points. It was, in terms of data collection, perfect. So perfect that it felt staged not by intelligence, but by extraordinary cosmic coincidence. However, instead of confronting or even acknowledging this improbability, the presenters treated it as a pleasant logistical convenience. They almost celebrated it. And while the tone was cheerful, the absence of curiosity was deeply concerning. In science, coincidence is never a conclusion. Coincidence is a spark, the beginning of a question. If a pair of dice lands on the same number 500 times in a row, you do not assume luck. You examine the dice. That is not suspicion. That is science. But the conference skirted around that line of inquiry entirely. The reason this matters is because anomalies are the birthplace of discovery. Every major shift in physics and astronomy, Newton's law of gravity, Einstein's relativity, the understanding of nuclear fusion, the discovery of dark matter began because something did not fit. When something challenges models, the correct response is not to smooth it over, but to lean into it. And here we had not one anomaly, but several stacked together, like aligned puzzle pieces waiting to be interpreted. If 3I Atlas truly has a nucleus 5 kilometers wide, or more, ejecting such an object from a star system requires energy on a scale that typical planetary scattering cannot provide. It would suggest one of several extreme origins, the aftermath of a planet-shattering impact. Tidal disruption by a binary star pair, violent gravitational expulsion from a giant molecular cloud, or some other rare cataclysmic event. None of these are impossible, but none are common. And if this object is indeed typical of some class of interstellar bodies, then everything we think we know about planetary system evolution would need revision. Yet none of this was mentioned at the conference. None of the presenters discussed origin scenarios, formation probabilities, or deviations from expectation curves. Not because they lacked intelligence, they are some of the brightest astrophysicists alive, but because large institutions do not handle uncertainty well. Bureaucracies prefer tidy interpretations. Data that fits into labeled folders. Objects that behave like expected objects. But science is not comfortable. Nature is not obligated to explain itself in bullet points and press-friendly answers. The role of the scientist is to embrace discomfort and dwell in the question. And to me, that was the greatest problem with NASA's public presentation. Not that they had incomplete answers, no one could be expected to this early, but that they did not show hunger to ask the questions. 3I Atlas is not merely an icy rock wandering between stars. It is a challenge placed on the desk of human knowledge. It is a reminder that with only 3 interstellar detections on record, we know almost nothing about the material traffic of the galaxy. Its size matters because it forces us to reconsider what is possible. The question that weighed heavily on me as the press conference continued was not whether 3I Atlas could be explained, but whether we were courageous enough to ask the right questions. Curiosity is the pulse of science, and yet I sensed a hesitation in the room, a desire to stay within the boundaries of safe conclusions and familiar categories. There is comfort in calling something a comet, even if that word does little more than prevent intellectual discomfort. But labels should follow understanding, not replace it. A major part of the puzzle was atmospheric chemistry. In most comets, observed within our solar system, the abundance ratios of metals, particularly nickel to iron, follow predictable patterns based on stellar nucleosynthesis. Heavy metals form during supernova explosions. Iron is produced in greater quantities than nickel, and their ratio remains consistent across the solar system's comet population. Yet preliminary spectral readings from 3I Atlas suggested something radically different, nickel in greater abundance than iron. To be clear, That is not something you see in frozen objects drifting freely in natural space environments. In industry, high-nickel alloys are prized in aerospace for their tensile strength and heat tolerance, but in nature they are extremely rare in free-floating cosmic ice blocks. Again, this did not imply anything artificial, but it did imply that the object's formation environment or geological history was unlike anything previously studied. One possibility is that 3I Atlas emerged from a region of a planetary system where metal separation had already occurred, perhaps through mantle differentiation or partial vaporization events that normally require substantial thermal or gravitational stress. Another scenario is that the parent body from which this fragment originated was disrupted during intense tidal interactions in a binary star system, where ferromagnetic and nickel-bearing phases could have separated before being ejected. Or, more dramatically, that the object was once part of a larger celestial structure that experienced catastrophic heating in the aftermath of a planetary collision. Each of these explanations would represent an extraordinary astrophysical event, the kind that shapes entire systems and leaves evidence drifting into interstellar space. Yet at the press conference, none of these possibilities were mentioned, despite the fact that the chemical data practically begged for such exploration. Equally intriguing was the reported behavior of the comet's jets. On comets within our solar system, outgassing jets typically shift or twist as the nucleus rotates. If the rotation period is 16 hours, one expects corresponding modulation in jet direction and brightness in that same cycle. But according to the images from multiple spacecraft, the jets on 3I Atlas appeared stable, straight, and consistent, seemingly unaffected by rotational modulation. This could suggest several things: an unusually uniform surface composition, a deep and energetically consistent vent system, or even an unexpectedly sluggish rotation, none of which were acknowledged publicly. Instead, the commentary focused on generic environmental interpretations, implying that the differences were merely the result of unique conditions in another star system. That might be true, but it glossed over the opportunity to dive deeper. A comet this large challenges the very physics of interstellar ejection. To throw an object 5 kilometers across into deep space requires immense energy, far beyond the delicate gravitational nudges that typically eject small fragments. If a planetary system can expel something this large, what does that imply about the forces operating there? And if this object was not rare in its original environment, then our sampling of the galaxy through interstellar objects is only scratching the surface of what is possible. The magnitude of the question demands investigation. Is our solar system atypical? Are we in a calm region of the galaxy while other star systems experience violent dynamism where massive chunks of planet-forming material are regularly launched into the void? Those questions lead to the greater philosophical issue at play, an issue that the NASA presentation did not directly address. In science, we form expectations based on observed patterns. If we assume that all planetary systems behave like our own, then we look for evidence that confirms that assumption. But 3I Atlas presents data that strongly suggests some systems may operate under principles, energies, or histories far more intense than ours. If so, it would not be the first time in scientific history that a small sample size misled us. Before the discovery of exoplanets, astronomers believed that compact systems like 51 Pegasi or the TRAPPIST-1 tightly packed world families could not exist. Before hot Jupiters were detected, we believed gas giants formed only in outer cold regions. Before other galaxies were confirmed, we believed the Milky Way was the entire universe. Overconfidence in small samples is not arrogance, it is human nature, but nature rarely respects our assumptions. One part of the conference did acknowledge that the most revealing data is still to come. As 3I Atlas approaches its closest distance to Earth, telescopes across the globe will aim their instruments simultaneously. Keck in Hawaii, VLT in Chile, Subaru in Japan, Hubble and Webb in space, and even dozens of professionally operated amateur observatories worldwide. At perihelion, the object's nucleus should brighten significantly. Sublimation rates should increase, and its structure may be exposed in unprecedented detail. If the object fragments, we will gain insight into its mechanical strength. If it remains solid, we may be looking at a body with internal cohesion far greater than fragile solar system comets. If non-gravitational acceleration is observed, we may learn about the scale and directionality of jet pressures. Everything hinges on the next phase of observation, and that is thrilling. Yet the press conference, even while acknowledging the data gathering, maintained a tone of settled interpretation rather than excited uncertainty. And that brings us to the larger concern that NASA is withholding information, but that large scientific institutions are deeply uncomfortable with ambiguity. Administrations prefer public messaging that conveys steadiness, reassurance, and the impression of having matters under control. That instinct is understandable, especially in a world where sensationalism spreads rapidly. But scientific truth is rarely neat. If something challenges our expectations, we should not round the edges to fit it into existing boxes. The public does not need false certainty. It needs transparency, even if that transparency admits ignorance. There is no shame in saying we do not yet know. In fact, that sentence is often the truest expression of scientific progress. The strange size, chemistry, alignment, and jet mechanics of 3I Atlas do not require extraordinary conclusions, they require extraordinary openness. Some will leap to science fiction interpretations, but the real wonder lies in the fact that ordinary natural processes might be operating in ways we have never witnessed before. If this object was born in a system far more dynamic than ours, then the universe may be filled with violent celestial factories capable of ejecting massive seeds across the galaxy. That alone would revolutionize theories about interstellar transport, planetary system lifetimes, and the mixing of heavy elements between star systems. Imagine if one day we confirm that planetary collisions are common early in star system evolution, and that the debris clouds from those impacts regularly produce fragments the size of small mountains, which drift between stars. Suddenly, the galaxy becomes a place of geological exchange, where worlds are not isolated islands, but contributors to a grand cosmic ecology. Elements, minerals, and chemicals torn from one world could seed the growth of another. In such a model, planetary formation becomes a galactic-scale recycling program. The implications for astrobiology, isotopic variation, and the emergence of life itself would be staggering. But none of those possibilities can be explored unless we ask first, how did this object come to be? 3I Atlas is, in this sense, a gift. It forces us to reconsider our theories and reminds us that our understanding of the universe is tiny compared to what remains unknown. When we first discovered exoplanets, the early examples shocked astronomers because they did not fit the solar system's architecture. 3I Atlas may represent a similar moment, not a threat, not a myth, not a harbinger, but a mirror showing how limited our expectations have been. And that is something to be excited about. The stakes are not merely academic. Every time we learn a new rule about how the cosmos builds and destroys worlds, we improve our understanding of our own planet's history and future. If massive interstellar fragments are more common than we assumed, then Earth may have been struck by such objects in the deep past, contributing elements or volatiles we previously attributed solely to internal processes. Or perhaps such collisions have been avoided, making our solar neighborhood unusually mild. Either answer would reshape planetary chronology. Looking beyond Earth, future generations of spacecraft may even be built with the capability to intercept interstellar visitors directly, land probes on them, and analyze their material firsthand. Missions like that are not science fiction, they are engineering challenges awaiting motivation. Rosetta and OSIRIS-REx have already demonstrated the ability to rendezvous with small bodies. Imagine scaling that mission profile to an interstellar nucleus several kilometers wide. The scientific payoff would be beyond measure, and 3I Atlas could be the first target if humanity takes that next technological step. But the first step is intellectual honesty. We must allow the data to speak, not through cautious press language, but through bold scientific inquiry. It is entirely possible that the press briefing avoided size estimates because the teams are still calculating margins of error. Scientists should not rush numbers before confidence is high. That would be irresponsible, but acknowledging the significance of the question, simply stating that size matters profoundly, would have demonstrated to the world that NASA recognizes the magnitude of what this object represents. Because in the end, 3I Atlas is not merely a cosmic rock drifting into the sunlight. It is a question, a profound one, and questions are not threats. They are invitations. The universe has placed one at our doorstep, and it is our responsibility to answer it without fear or premature closure. We should remember that every breakthrough in science, from the discovery of exoplanets to the detection of cosmic background radiation, began not with answers, but with anomalies that did not fit accepted models. The willingness to confront those anomalies without flinching is what separates progress from stagnation. When I look at the images and data coming in from across the fleet of spacecraft, I do not see doom or mystery. I see curiosity reshaping itself. I see an object that refuses to fit neatly into human assumptions, and because of that, it has the potential to teach us something profound. If the universe hands us a puzzle, the correct response is not to hide the strange pieces, but to examine them with patience, humility, and an open mind. 3I Atlas may eventually prove to be perfectly natural, but natural does not mean ordinary. It may show us that planets and stars form in ways we never anticipated. It may require us to update the textbooks once again, or it may reveal an entirely new category of interstellar debris, larger, denser, and stranger than anything we have cataloged before. Whatever the final answer, it will only be found if we are willing to ask the questions the data demands. The size matters not because it makes the object impressive, but because it forces us to rethink what we thought was possible. And that, more than any photograph, spectrum, or press release, is the heart of science. The courage to let the universe surprise us.